We will begin with a review of the last class topics. If you can recollect, we looked at first level interconnections. And what are those first level interconnections? Basically, it is wire bonding or wire bond. The second one is tape automated bonding or TAB, and the third one is flip chip. So, these are the three basic chip connection choices, and they form the first level interconnections. Before that, we also had a look at what is the definition for pitch, right. So, if you have two I/O points, the midpoint of these two adjacent pins or pads is referred to as the pitch, and we have seen as the decades went by, starting with the TO CAN, and today we are in the CSP, okay, or wafer level package. We have seen that the pitch has decreased tremendously, and that is one of the reasons why we are able to get new formats, okay, and lower sizes of packages and more I/O pins that have been packed into these packages. So, this talks about package density, and it can also get reflected in the assembly process that we are talking about. So, if you can recollect, we talked about TO CAN, then the development came into what is known as DIP packages or dual inline packages. Then came the QFP packages called quad flat pack packages. Then came the pin grid array PGA, pin grid array packages that are used in or that were used in a lot of microprocessors. Then came the migration to ball grid array BGA packages, and finally, today we have what is known as the CSP class of packages. This is called chip size or chip scale package. So, this is what we saw last class, and we also briefly mentioned about the term called epoxy resin, because I have shown you different samples of single chip packages in which I have showed a molding compound that is being used to protect the first level interconnections. That means, you use an organic resin to cover up and protect the first level interconnections like your wire bond or your tab or the flip chip, so that they are protected from the environment. So, this is some sort of a protection, or you can call it as encapsulation. So, organic chemicals are used, organic resins are used, and one of the most common resins to be used today is epoxide, that is the chemical name, which has come to be known as, very commonly known as epoxy. So, I will be using this term called epoxy quite a few times, and I will also explain why this is necessary for protecting your packages. So, I will start first with telling you the different application areas for using epoxy resin. So, if you look at this slide, there are various application areas in this packaging industry which can utilize epoxy resin. It is not that epoxy is the only material that needs to be used for these purposes. There are other materials also, but they can be expensive, and each of these exhibit different physical and chemical properties. So, in the industry where large volumes are used, obviously, you will look at economics, you will look at low cost and ease of handling. So, that is probably one of the reasons why the most common material used is epoxy resin. So, epoxy can be used for molding purposes, encapsulation purposes. the term potting sample also refers to a methodology where you can use epoxy material to mold certain compounds for analysis, to look into various aspects of surface topography or inner layers of a built up substrate and so on. So, it can be used for package encapsulation. It is also used as the material for underfill media. As I briefly mentioned, when you use a flip chip material, a flip chip is a die which has got bumps underneath, and when you mount it on a substrate, organic substrate or a ceramic substrate, there are bond pads on the substrate which you will register with the flip chip, and the area between the die and the substrate is protected with underfill. So, this underfill material is also an epoxy material very commonly used. We will see why underfill, what if you do not use an underfill in the coming lectures. This particular slide is basically to tell you the different application areas for epoxy. It can also be used as a photo imageable solder mask material in the printed circuit board industry. It is also used as a key ingredient in the manufacture of printed wiring board substrate. So, I want to show you a sample of a blank printed wiring board substrate here. Okay. This is a substrate without copper on both sides. So, this is basically an epoxy material. This is a very rigid material, very hard material. You can also get flex epoxy materials. As I mentioned before, there are different classes of substrates used in the PCB industry. So, I am giving you the best example in terms of low cost and ease of operation. So, it can be used as a substrate for printed wiring board. It can also be used as a conformal coating for finished printed wiring board assemblies, and it is also used in chip on board technology. COB is known as chip on board technology, where it is used as a glob top. I will give you an example. For example, if you have a substrate and if you have a die mounted on the substrate with the bond pads on top, you are going to do a wire bond like this. Now, after the wire bonding is done, you protect it with a glob top. This is epoxy. Okay. So, this is used to protect the first level interconnection. So, you can use it in wire bond and tape automated bonding. It is also used as a media when you are using conductive adhesives. Normally, when you want to attach a die to a substrate, you use a non-conductive adhesive, but in the PWB or PCB assembly, we are going to talk about how we can use conductive adhesives for establishing second level interconnections, okay, and it can do away with a lot of soldering processes. It can also be used as a solder paste media in the PCB industry, and like that there are different examples. So, basically if you look at this figure here, the chemical structure, you can see that this is the active epoxide group. So, basically it is CH2O CH2, and you have the epoxy ring here which is very active, and you can have a long chain polymer coming out of different organic structures having epoxy rings. So, it is known as epoxy or polyepoxide. It is a thermosetting polymer. That means, once you heat it or cure it above a particular temperature, it is very difficult to bring it back to its original state. And this curing is normally done with the use of some kind of a hardener which will change the properties of the material. And for the substrate that I have showed recently, the epoxy resin is basically from a combination of bisphenol A and epichlorhydrin, which in the next slide I will show what is the actual reaction taking place. And there are different manufacturers for epoxy material. I have just listed a couple of companies here. There are many companies manufacturing epoxy resins for the packaging industry. Epoxy is not only used for electronics industry, it is used for other industries also as a binding material, as a curing material, as a sealing material. So, if you look at this reaction here, the laminate structure which I showed you as a sample here involves basically formation from a reaction between bisphenol A chemical and epichlorhydrin, which contains the epoxy ring, epoxy group, okay, in the presence of sodium hydroxide, and therefore, you get a long chain polymer. Here the N, the number of elements here, the N is equal to, depends on what kind of molecular weight you require. So, this can be established by defining the weight of the materials that you have taken, that is the starting materials, and the time, the temperature, the conditions, and what kind of molecular weight you require as an end product to define your application. Okay. So, this is a repeated unit that will be defined by the conditions of the reaction. So, once again I want to emphasize and tell you, and at this point you should be able to very clearly distinguish between what is a glob top and what is an underfill, because these are two things that we are going to use in this industry. So, I will basically show by a quick diagram how you use a glob top. Although I have explained it more than once, I think it is better to do it. So, assume this is a PWB or a printed wiring board, printed circuit board, if you can call it. So, this will be a multi-layer structure. Now, here you are going to place a die, a known good die, on top of which your bond pads are established or the IOs are established. Now, peripherally you do a wire bonding, So, you require bond pads on the substrate also. Now, you check your wire bonds for electrical contacts. Now, for this particular bare die where the face is up, this is a face up configuration. Okay. So, similarly for other wire bonds you will be doing the connections. Now, you apply using a syringe or some other dispenser, you apply this epoxy resin and cover the entire wire bond structure that you have generated. So, this is a protected area. So, this is known as glob top. I hope you are clear with this explanation about when to use a glob top configuration of epoxy resin. In the case of underfill, so you have a flip chip. What is a flip chip? It is a chip that is flipped over, which means when you flip it down or flip it over, you have the bumps. This is the flip chip. It is a bare die. Now, you have a substrate on which this is mounted. Okay, this can be a printed wiring board. Now, the bumps will touch the bond pads on the substrate, and using heat, using pressure and using ultrasonic energy, or simply by using a reflow process. Reflow is basically remelting the solder material that is there in the bump of the flip chip. Now, a connection is established between the bump of the flip chip and this bond pad on the printed wiring board. Now, there is a small gap between the die and the PCB. So, basically you need to cover up this area, so that the die is protected and the established new connections are protected. So, what we do is we use this epoxy material, okay, and apply in between the area of the die and the substrate. So, it will take a shape like this. So, the underfill will be dispensed in the area between the die and the substrate. So, this is known as underfill, For this also we use epoxy material. Having seen wire bond, now we will see what is TAB, tape automated bonding. Tape automated bonding or TAB is basically an interconnect structure patterned on a tape. So, as you can see in this figure here, this is a tape. This tape has got these kind of perforations that you can see, because this is required for mounting on the equipment. This is basically an equipment based operation, automated process. It has got stronger lead bonding strength, because basically instead of a wire we are going to use thicker leads. The lead materials can be different. It can be made out of gold, it can be made out of other materials like covar, invar, or it can be simply tin lead plated materials. So, basically we are going to use leads, and it supports smaller on chip pin size and pitches. It supports up to 850 pins, and it has got better electrical performance than wire bonds. And typically the advantage of using TAB is that you can increase the number of IOs compared to wire bond structure. And wire bond today is automated, but at the same time it is a very sequential process, whereas here it is somewhat a different assembly process. So, TAB is an approach to fine line pitch interconnections of a chip to a lead frame. So, basically you are going to use a lead frame structure like your dip package. The interconnections, so you can see in this figure that these are the lead frames on 4 sides of the tape. This tape is basically a plastic material. Typically we use polyimides, okay, or some other form of plastic material. Now, in the center here you see the die. Okay. So, there are 3 entities here. One is the die, the other is the plastic material or the tape that you see here. The third one is the lead frame, which houses the leads, which are basically the input output pins connecting to the external world. And then this die is brought into registration or into the exact position that is required, and that is defined by the lead frames present. So, you can imagine this tape sitting here and your die is coming from underneath and aligning with the lead frames. Now, from the top you use thermocompression bonding. That means, you apply heat, you apply pressure, and then the lead frames will bond with the bond pads on the die, and then a connection will be established. Okay. So, this is a second chip connection choice that we are discussing after wire bonding. So, I think this picture is much clearer. You can see here at the center, the die, the blue color material is the die that is coming from underneath, you can imagine, and this material here is the polyimide tape, which has got perforations because it comes in reel form and it needs to be attached to the TAB equipment. Then these are the lead frames that you can see here. Now, using thermocompression bonding from the top, you can establish connection between the lead frames and the bond pads on the die. So, this is known as inner leads, and here this is known as the outer leads. So, a TAB process will involve 2 types of bonding. First one is inner lead bonding and the second one is outer lead bonding. So, you have inner lead bonding and outer lead bonding. So, you need to understand what is inner lead and outer lead bonding and what are the temperatures, methodologies and conditions for establishing this bond. Now, where is tab used? Typically, you can use tab in the manufacture of smart cards. These are used in phone cards, ID cards which use RF, etc. Pocket calculators, digital radios and so on. So, you can imagine now that tab is used where the product size is very small and typically you have just one die that is required to be connected to a lead frame structure that will establish connection to the other parts of the circuitry. So, tab will involve first an inner lead bonding process and after that is checked, then the outer lead bonding process is established and the extra material of the polyimide is then removed by cutting or removing it from the equipment. So, that is tab. Now, we come to the third chip connection choice which is known as flip chip process. It is also known as C4 process. C4 means controlled collapsible chip connection. Okay. C4 is known as controlled collapsible chip connection process. In fact, flip chip or C4 is not a new process. It has been established by IBM way back in 1963, but the developments over the years have brought flip chip to the forefront today as compared to tab and wire bond. Of course, wire bond has been used for a very long time in all your DIP packages and QFP packages where the profile is very high, but today with low profile components you are not able to use wire bond because it occupies more space, more volume. So, compared to wire bonding, as you can see in this figure here, I think now you are very familiar with the peripheral bonding of wire bonding. As you can see, the bonding of wire bonding process is at the periphery and here these are the gold or aluminum wires which is attached to the substrate. So, the flip chip process once again is flipping the chip over and these have got bumps. Now, what is the size of these bumps and what is the material of these bumps? The size of these bumps is around 100 to 400 microns, but today more standards or the most common standard is around 125 to 200 micron. Now, the pitch is also very similar. The pitch is also very similar. So, you can imagine the difficulty in establishing a flip chip bonding even if it is through a sophisticated equipment. You have to have very good registration procedures in the equipment to establish a very good flip chip connection. Now, this is the die and it is flipped over. The material that is used in flip chip is basically tin lead or other tin based material if you do not want to use lead, because lead is a health hazard. So, you can use tin, silver, copper or some other form of material used involving only tin and indium or tin bismuth and so on. We are going to look at these things at the latter part of this course. So, you require a substrate. So, once you have a flip chip ready to be assembled, next what you require is a substrate, and the requirement for this bonding is the substrate should have bond pad which is also very small in size, matching with the area or the area of the solder bump. Now, you apply heat, you apply pressure, okay, and you can also apply heat to the board or the substrate. So, that using thermocompression bonding you can establish a connection with the two components, and then you apply an underfill material to protect your substrate. So, this is a method to electrically connect the die to the package carrier. The bond wire here is replaced by a conductive bump placed directly on the die surface. So, the bumping process itself is a technique which we are going to look at very shortly. So, when you use a flip chip, you will have to look at the materials used in the bump, because only then you can characterize the reliability, you can understand the reliability of the solder joint established by the flip chip. And also you need to characterize different types of materials that are used in flip chip. So, you need to have a very good understanding about the bump material, the substrate material, and the basic thermal mismatch that can happen between the bare die, which is silicon, and your organic substrate if you are using economic organic substrates. So, you can use underfill epoxy to protect the die and the substrate, because there is going to be stress when the board is in operation or when the chip is powered up. There can be heat that can come from the chip, which can, if it is accumulated, it can crack the die, it can warp the substrate, it can affect the solder joint. So, the chip is flipped face down, as we have seen here, using a reflow process. So, in addition to thermocompression bonding, you can also use a reflow process. Reflow basically means you are going to melt the solder bump again and establish a new metallurgical bond with the bond pad on the substrate. The bump sizes range from 90 to 150 or 125 microns in diameter. So, you can imagine that this is a very high dense connection. This is not a package, mind you, flip chip is not a package, and you need to have a fairly good understanding if you want to use C4 or flip chip. Now, where is flip chip used? Flip chip is used in the manufacture of ball grid arrays and CSPs. Okay. So, either you can use flip chip use, one can be as a chip on board directly onto your substrate, it can be used in the manufacture of BGA packages, or it can be used in the manufacture of CSP packages. Okay. So, the whole chip area is available for I/O connections, that is how the density increases. Automatic alignment, and it is a one step process. I want to explain to you what automatic alignment means. Now, if you look at this figure here, there is a die and this is the bump and this is your substrate. Now, we are going to align this die with the substrate. Now, this bump is basically a solder material. Now, when you apply heat to the process, assume it is a reflow process, you are going to apply heat. What will happen? The solder will melt. The solder melts, and because it is a melting process, the flip chip the chip will try to move away from its position slightly. Okay. But the surface tension of the solder material in conjunction with the bond pad area and the bond pad material will pull back the die to its original position. So, there is absolutely no reason why you will have misalignment during the reflow process of a flip chip, because of the automatic alignment provided by the surface tension of the solder material and pulling back the die to its original position, you will get 100% perfect alignment, and that is how the yields are very high. So, the automatic alignment actually provides you a much better yield compared to other processes. It is a one step process because all the connections are established at one time during the reflow process. The cooling of the entire die takes place through the solder bump material, okay, and also from the top of the die. So, this area is also utilized for cooling because it is exposed to the atmosphere. There is always a question of thermal mismatch between the silicon here and this is a plastic material. So, there is going to be a thermal mismatch. We will see how we can remove or minimize this mismatch. Of course, one important thing that takes care in minimizing the thermal mismatch and protecting the die is using a underfill material. Okay. So, a BGA or a ball grid array can be fabricated either by using a wire bond structure or by using a flip chip structure. So, there are two methods to create or manufacture or design a BGA ball grid array material. So, in this case, the first case, there is a die here, there is a die here, there is a wire bond that takes place to the bond pad on the substrate, similarly at the periphery, and then there is a substrate which is high dense and which provides the solder balls at the bottom, providing the second level interconnect. And in this case, it is a different process altogether. So, a flip chip is not a specific substrate material, you must be clear about it. This is not a specific package like SOIC, small outline integrated circuit. This is not a package. This is not a specific package type like QFP or a BGA or a pin grid array. This is basically a chip connection choice. Please do not confuse a flip chip with a package. It is not a package at all. It is a first level interconnection choice, and it can be mounted on organic and ceramic substrates. In other words, it can be directly used at the printed circuit board level, like your chip on board. When you say board, you can use it as a chip on board activity. So, where can we use flip chip? What are the application areas for flip chip? Flip chip can be used on boards where it is used in, let us say, digital cameras, or camcorders. It can be used in laptop motherboards. It can be used in communication handheld products. Okay. So, flip chip combined with a BGA or a flip chip in a CSP format are the most favored package choices today for application areas in these various segments: cameras, camcorders, laptop, handheld products, various handheld products. Okay. So, what we have seen now is the summary of all the first level connection choices. We have seen exclusively what is a wire bond, what is a tab, and what is a flip chip or a C4 process. Now, what I am going to do is give some more inputs to you on each of these first level connection choices, so that you can understand the process sequence. How do you do wire bonding? Wire bonding is used in interconnecting the die to various substrates, and it is the most popular interconnection method. So, it is a solid phase welding process where the two metallic materials basically are going to use a thin wire, and the thin wire can be gold or aluminum. Today copper is also used, and the metallization on the pad surface is also ready for this bonding process. So, on one side you have a thin wire, on the other side you have a pad surface that is ready to take up the wire, and these are brought together in intimate contact by the wire bonding process using a combination of heat, pressure, and or ultrasonic energy. So, you can decide what combination you want to make the process simpler without providing too much heat that can damage the substrate. So, depending upon whether you are using gold, you can use a thermocompression bonding. If you are using aluminum, you can lower the temperatures and so on. So, wire bonding is of two types. One is known as wedge bonding, the other is known as ball bonding process. The wedge bonding uses a wedge tool. So, here the tool is a wedge tool, and here in the ball bonding process you use a capillary where you can draw thin wires. Okay. The wire diameter depends on the space availability and the area that is available. If you are using a chip on board, directly on board, probably you can have more area to utilize, but if it is in a package on a lead frame, then you have to be very critical in choosing the diameter. So, the improvements over the years have been due to the increase in the wire bonding equipments that are available, because the speed of wire bonding is very much essential to increase the volume output in a commercial manufacturing setup. But today every wire bond is almost highly inexpensive. It is about a cent or less than cent per pin. So, the bonding tools are of two types: wedge and capillary tool that is used for bonding. Wedge tool utilizes aluminum, and you can see the shape of the wedge tool, which is flat and larger, and capillary comes of different sizes depending upon the diameter of the wire that you want to draw. Typically gold is used for capillary ball bonding. So, here you will use ball bonding process, and the classification of the entire bonding can be thermocompression, ultrasonic or thermosonic. If it is a combination of heat and ultrasonic energy, then it is known as thermosonic bonding. Now, aluminum is more suited for wedge bonding. The reason is aluminum is fairly easy to work with mechanically compared to gold. And if you can look at this figure here, what I am basically trying to show you is a wedge bond that has been formed using aluminum wires. Now, this is the silicon die here, as you can see it is labeled. Then this is the wedge bond from the bond pad on the silicon die to the lead frame, let us say, or the leads of the package. Now, you can see a wedge has been formed, and at this area you can see the connections are fairly large. It requires larger area and size. So, basically you cannot expect too much of a high density using wedge bonding process. What are the process steps for a wedge bonding process? Now, the wedge tool, the tool that you saw earlier, this one is loaded with the wire, typically aluminum. Now, you apply pressure and ultrasonic energy. The reason for using ultrasonic energy is you can reduce the temperature of operation, because ultrasonic vibrations and the ultrasonic energy will require a minimum amount of energy in the form of heat. Otherwise, the actual operation for wedge bonding will be much larger, temperatures will be larger, it can affect your substrate. So, you apply the pressure, required pressure and ultrasonic energy to form a wedge. So, bonding is done first on the substrate pad, then a loop is formed. This is basically the loop. Now, this as an experienced person, you will decide how much loop and height you require for forming a wedge bond. After the loop is formed, then the package to bond formation here will be done. So, this will be the first site where the wedge bond will be formed, and this will be the second site where the wedge bond will be formed. And finally, the wire is broken off here, okay, This is the start point and this is the end point. So, that completes the wedge bonding process. Now, this has to be faster in the industry if you want to have more throughput from the wedge bonding process. Now, let us see what is a ball bonding process. Obviously, as the name indicates, you have to form a ball of the gold wire. The most popular material for ball bonding is gold. The capillary is loaded with the gold wire depending upon the thickness that you want. It can be ranging from 50 microns to 300 microns depending upon the bond pad area available and the peripheral number of connections that you have. Now, you can create an electronic spark, electronic flame of wand will generate a spark, a high voltage spark that will melt at the tip of the gold wire to form a ball. So, basically I will show you a video clip which you can understand, but basically there will be a wand and there will be the wire that is coming and this will melt the wire to form a ball. Okay. And this molten ball will now be utilized here. So, you can imagine that this molten ball is here at the first bond site on the die. Then using appropriate pressure and ultrasonic energy or a combination of heat, pressure and ultrasonic energy and the ball formed, you form the first bond here. Now, you take a loop. So, this loop height is very important and the loop length is also very important. There are various calculations that are required to determine or fix what loop height you want and what loop length is. Actually, this is determined by the two bond pads. This distance is fixed. So, according to this, what loop height you require is dependent on the thickness of your gold wire. Then after the loop is formed, the package bond pad formation is done here at this point and this is known as a stitch bond. This is not a ball bond, this is more like a stitch formation. So, that completes the two ends of the wire bonding. So, the first one is a ball bond and the end one is a stitch bond, and then here the wire is broken off to complete the process. So, this is the cross section of a single chip package. This is a QFN package, quad flat no lead package, QFN. As you can see here, it is a cross section. You can see the lead frame at this point. You can see this is the area where the heat will be dissipated to the substrate. So, this is an exposed thermal pad. There is a die attached material glue that bonds the chip to the substrate. Then you have the wire bond here. Wire bonding is done on both sides, peripheral. This is the die and then this is the encapsulation. This part is the encapsulation. So, you must be able to now draw such cross sections for a wire bond BGA, for a wire bond QFP, for a flip chip BGA and so on as we go along. So, this is a pictorial depiction of the wire bonding process. You can see here there is a clamp, there is a capillary and then comes the ball formation. The ball now touches the pad surface, the formation of the ball, there is an ultrasonic energy, there is a pressure, okay, and that reduces the temperature. The ball bond is established. Now, the clamp is pulled over, the loop is formed. This is the loop. The loop is formed, then taken to the next site. This is the lead frame or the package. Okay. So, this is the second landing site for the wire. So, a crescent bond or a stitch bond is formed and then it is cut off. So, this is a picture showing you how a spark, high voltage spark will create a ball. and that is now utilized to form the first bond. So, the wires for wire bonding can be gold, it can be aluminum or copper. The pad that is required for leading the wires to form the attachment can be made out of aluminum, gold, silver, nickel and copper. Die bond adhesive is used to bond the die to the substrate, and that adhesive is basically a epoxy organic polymer. So, this picture shows you a micrograph of a ball that is created. This is the commercially available wire which you can utilize for wire bonding. So, this is typically aluminum, but you can also get gold or different sizes and diameters, and this is the crescent or the stitch bond that you can see, which is used in the second step of the wire bonding process. Okay. So, the loop height is determined by the diameter of the wires, and the normal test after wire bonding is done is basically to pull the loop and look at the loop strength. Okay. So, there are certain standards that you can look at in the handbook, and you can determine the quality of the wire bond. So, typical guidelines are given here for 20 micron and 25 micron wires. The shear force is around 12 grams and the shear strength is about 6.5 grams per mil squared. 1 mil is 25.4 microns. Okay. So, like that, if you can look at for different materials and different thicknesses, you can do quality tests in your own lab if you are doing wire bonding at your laboratory. Now, I would like to show you a video clip of a wire bonding process. This is die bonding, which I am going to show. As you can recollect, die bonding is basically attaching a die, a known good die, a silicon die to a substrate. So, what you have seen in this video is a glue, an epoxy material is dispensed using syringes. It can be done by other methods also onto the area or the substrate where the die is going to be placed. This is a non-conductive adhesive. This is used for all the first level connection processes, like for wire bonding. Before wire bonding, you have to do a adhesive bonding, except in the case of a flip chip, where you do not require a adhesive bonding, because your solder bump is going to be flipped down and that will establish the connection with the substrate. Now, what I am going to show you is a video clip of a wire bonding process. So, you can see the wire bonding process in the industry is highly automated. the throughput is very high, the number of hits or number of wire bonds established per minute is very high, and that is how your yields in forming the packages, first level interconnections, are a very high benchmark that is set by the industry today. So, this also poses a very big challenge for the equipment manufacturers, because they also work in close tandem with the package assembly people. Now, I will show you what we have seen earlier clip is basically high throughput wire bonding process. Here we will see the individual bonds, that is ball bond, wedge bond, and another type known as ribbon bonding.
Ball bonding is a technique for interconnecting silicon chips. Here we see ball bonding on 200 micron diameter aluminium wire. An arc is used to produce a ball on the end of the wire. The ball end allows a multi-angular bond placement approach. It's pushed down and ultrasonically welded to the chip. The wire can then be led to a lead frame or the substrate and wedge bonded. The process is normally used with gold wires. Wedge bonding is used mostly on aluminium wire and is a reliable method of joining silicon devices to substrates and lead frames. Both processes can be automated to achieve speeds of 3 to 10 loops per second. And here we see ribbon bonding, which is used primarily in high-frequency devices.
So, you can see that wire bonding process in the industry depends on a high throughput. Typically, we are looking at something like 60 to 70 hits or wires per minute. Okay. So, it has to be very fast and it has to be accurate, and all the processes are to be in tandem. If it is a ball bonding process, the formation of the ball, the formation of the loop, and then the stitch bond at the other end should occur in perfect tandem and without any misalignment. So, the features of wire bonding is it should be high speed, economical, strong bond, quality, reliable bond. So, obviously, you have to do some post wire bonding quality checks continuously. The bonding pad area depends on what type of material you are using. If it is a wedge bond, you require more area. If it is a ball and stitch bond, you do not require that much area. For example, if it is a 2 mil gold wire, as I said, 1 mil is 25 microns. If it is 2 mil, then you have to use about 5 by 5 mil pad, okay, to establish a reliable connection. Ultrasonic bonding can be used for aluminum wires, and thermosonic works at 150 degrees centigrade, faster bonding time. Okay. So, you have seen now thermocompression bonding, ultrasonic bonding, and thermosonic bonding. Here the pressure used is high, low pressure, temperatures between 300 and 500 degrees centigrade, whereas if you use ultrasonic it can be much less. Okay. So, that depends on the material that you are using, and in thermocompression bonding you do not use ultrasonic energy. Here obviously you are using ultrasonic energy, and the wires used for thermocompression bonding typically is gold, and for ultrasonic it is aluminum, thermosonic it is gold, and the pads, the bond pads typically have to match. Typically for gold you can use aluminum or gold, but today if you are using wire bonding on printed circuit board, you can have nickel gold as the surface finish for wire bonding. Bond failure can always happen. There can be fatigue related to wire bonding because of temperature cycling, or basically when you power up the chip there can be effects caused by heat. So, typically you do a temperature cycling to qualify the wire bonds. Impurities can creep in because of various materials that are used, the impurity of the host material. There can be interdiffusion and that can lead to failure of the wire bonds. That can basically reduce the strength and can increase the fatigue, okay, of the wire bonds. Wire failure, wire flexure, vibration fatigue and eggshell fatigue, that depends on the application. Corrosion from the materials that are used and the harmful effects of the intermetallic growth materials that have been formed. So, basically you have to do testing, ball bond shear test or the destructive pull test after the bond has been formed, and other mechanisms like random vibration test, because wire bond is subject to fail during vibration. Accelerated test as per standards, that means HAST stands for highly accelerated stress test, where you set up certain temperature and humidity conditions as per the standards. It can be military standard or other industry standards, and look at how your wire bonds perform or survive. And you can also do standard mechanical shock tests, vibration shock tests and testing for corrosion. So, today we will end here. We have covered all the basic first level interconnection choices in detail, and in wire bonding we have also seen the complete process flow. The next class we will start with the process flow for tab and the flip chip. Thank you.